Well, hello guys. In today's video, we are going to make this creepy matrix style ASCII mapping or shader in Unreal Engine 5. So let's get right into it. So first things first, we are going to create the material by coming into the content drawer and right-clicking, clicking on material and calling it whatever you like. I will call it PP for post-process and matrix ASCII or something. Open up your material, and the two most important things are to set the post-process for the material domain, and in the post-process material blendable location set it to scene color after tone mapping. Now let's see a logical overview of what we are going to do today, because it might seem pretty hard, but it's actually pretty easy. So as you can see, we have our standard UVs, which is the whole screen. We are going to divide that into squares, and we are going to get this pixelated grid of our screen. Now after that, we will calculate the brightness of each of these pixelated squares. And after that, we are going to import a texture of an ASCII matrix or this ASCII list. And then we are going to map each of these ASCII characters based on brightness. So that's basically the whole logic. So let's get into the shader. We will need our ASCII matrix or texture, for which I am going to leave a link in the description to this site, and also the exact string I used for my shader. But if you can find any more strings or the strings that work better for you, this is completely alright. So you're gonna need to set the bitmap width and height both to 1280 and the cells per row and cells per column to 10 and 10. And then you're going to go into the description and copy this exact string and paste it down here to the character set string. And as you can see, these katakana characters at the end aren't being printed. That's because we have to set our font to Noto Sans JP. And as you can see, the Japanese characters appeared at the end. So these are in order by their density, and we are gonna set our font size to around 100, but as you can see, some of the characters are blending into their neighboring grids, so we are going to lower this font size until at least the majority of the characters aren't bleeding or blending into their neighbors. Once you've done that, you can save the image and hold it and drag it into your content drawer. Once you've imported this texture, we have a few settings we have to set here. First of all, this is the most important, make sure that you set the MIPGen settings to no mipmaps. This makes sure that Unreal doesn't blur the texture when projecting it to the screen. And after that, the compression settings should be user interface 2D. And the third one is the filtering. You have to set this to nearest. Once you've done this, you save and you can close your texture. So now we can get into the blueprint stuff. So first of all, we are going to make the pixelator, or the pixelator. We are going to get our screen position, and this is going to output a smooth gradient over our screen from 0 to 1, or 0 0 in the top left and 1 1 in the bottom left. We are going to need a scalar parameter. You can create by holding down S and left clicking, and we are going to call this grid resolution. Go ahead and set this to around 150, but you can change this later if you don't like. And we are going to multiply our screen position by this grid resolution. Next, we're going to need a floor node. This floor node will round the decimal values down. So, for example, 90.1 becomes 90, and 90.9 also becomes 90. After this, we just need a division, and we're going to drag our grid resolution into division, and basically the pixelation logic is done. So I'm just going to comment this and call it pixelation. Next, we have to get the average luminance of each of these cells on our screen. So we are going to need a screen texture. Oh, sorry, scene texture. And for the ID, you're going to set post-process input 0, which is the screen that the camera sees, or the post-process sees, and connect the division result to its UVs. And after this, you are going to desaturate this, because as you can see here, the image is colored, in which case the engine will not be able to tell the average luminance. So we need to desaturate it, which basically is just takes away the color. As you can see, it's now black and white. After this, we're going to need a mask, and mask the GB and A, so we only have the R value. And we can comment this as well and call it luminance. Nice. So we're basically done with mapping the screen, and now we can move on to mapping the ASCII table we created at the beginning of the video. How are we going to do that? We are going to need a few scalar parameters. Namely, the first one is going to be max index, and this will tell our shader which is the highest index in the table. Since we have a 10 by 10 grid, which means the highest number is 100, but we are going to set this to 99, because in coding the counting begins at 0, so we have 100 numbers from 0 to 99. Okay, next up, we are going to multiply this value, the masked and pixelated screen. We are going to multiply this by the maximum index on the grid. And why do we do this? For example, if the darkness value on the screen, which we get from here, is 0, we multiply that by 99 and we get 0. And on the other hand, if the value we get for the luminance is exactly 1, then we are going to have the 99th number. So if you're a bit smart, you could have guessed that this is going to be our character index on our ASCII grid. So this little logic here will tell us which character from the ASCII table to print on the corresponding luminance value on the screen. So now we have to create our ASCII table map, which will tell the shader where to find these characters on our ASCII map. So first, we are going to create the rows. We need a divide and another scalar parameter, which we will call atlas row, which is basically the row count that we set on the website in the description. So because we set it to a 10 by 10 grid, we are going to give this a default value of 10 and pass it to the divide. And we are going to need to floor this because this is the row. Why do we need to floor it? Because let's say that the character index we got is 12. But if you divide 12 by 10, you get 1.2. But on the ASCII grid, which we are going to pass in on the end, there isn't a 1.2 row. So we need to floor it down to 1, and that will tell the engine or the shader to search in the first row. Next up, we are going to create the column, which we are going to do by creating an fmod node. And into this fmod node, we are going to pass the exact same atlas row variable. And basically what this fmod does is it's a remainder division. So if we pass in the aforementioned 12th, or if the luminance value for us and the character index calculates a 12, and we divide that by 10, the result is going to be 1, but we actually need the remainder of it, which is 2, and that will tell the shader to look in the second column. So now you can comment this and call it column. Nice. We are almost done here. We just need a few more things. So come back to the beginning and find your screen position multiplied by your grid resolution. And we are going to create a fraction node and connect our multiply to it. And basically the fraction just removes the whole number and keeps the decimal part of it. So for example, 1.2 becomes 0.2. And why do we need this? Because as you can see, when I preview this, our screen, it's a little hard to see, but if I put the value of 10, as you can see, our screen position became these tiny little grid, or became this grid with these values that are ranging from 0, 0 to 1, 1. And this will allow us to draw a full texture from our ASCII grid into each of these. I'm just gonna put this back to 150 and take this fraction node all the way to the end. I'm gonna create a reroute node here just to keep everything nice and organized. And you take your fraction node all the way to the end, and you are going to combine the x and y coordinates by an append vector, and this is going to create the exact coordinate for the shader. So this is going to make the x and y value into one vector, and you're just simply going to add the fraction to the appended vector. Nice, guys, we are almost finished, actually. And now we are going to normalize this whole thing, which is going to make the difference. We are going to divide this result of this addition by the atlas rows. And why do we do this? It is because our coordinates are going to be big. For example, 2.5. But the UVs must be from 0 to 1. So by dividing by 10, we ensure that all of the numbers that we get from all this here from the beginning are going to be between 0 and 1, because as you remember, we set our grid to a 10 by 10. And now comes the fun part, because we are going to put a texture sample node here, and the engine was kind enough to fill it in for me. You're just going to take your ASCII map texture and connect the division result into its UVs. And with this, we basically mapped our screen to the ASCII table. And now comes the matrix part. We are going to multiply this by a 3 vector, which you can create by holding the number 3 and left clicking, and we are going to convert this to a parameter and call it, I don't know, color maybe, and set this to the good old matrix green and connect it into the B for the multiplication. Yes. And after that, you can drag your multiply into the emissive color, and as you can see, if you've done everything right, you have the ASCII table mapped onto your screen. And now, how do you apply this into your world? You just come here and get a post process volume and check infinite extent unbound. And I like to do one more thing, which is searching for the exposure and ticking the metering mode and exposure compensation and setting the metering mode to manual and the exposure compensation to 10. And I'm gonna show you in a minute why I do that. But before, you are going to search for material and add a process material asset reference, and then plug in your pp matrix ASCII. And once you do that, the whole screen becomes this matrix. So now we have completed it. Oh, and yes, why do I set the metering mode? It's because when the metering mode is on automatic, as you can see, it creates these circles which are expanding and then shrinking, and that's because the exposure is automatic and it dynamically changes or adapts like your eyes in real life to the environment. But if I set this to manual, as you can see, everything becomes static and the circles don't move around anymore because the luminance values aren't changing when you get into a dark place or you go out in the light. So that was it for today, guys. Thank you so much for watching, and as always, let me know in the comments if you liked it or if you need any other tutorials. And yeah, Like and subscribe if you want. And thank you so much for watching.